Sounds like I'm getting some rumble. Okay, is that better? All right, thanks for coming here for my presentation. I'm Joel Kastner. Dima and I agreed I just introduced myself. I've been a member of the faculty for 26. This is my 26th year here at RIT with the imaging science program, and last 15 years or so with the astrophysical sciences and technology program, PhD program as well, graduate program. And before that, I was at MIT for about 9 years. And before that, I got my PhD from UCLA and my bachelor's before that from the University of Maryland. So that's my pedigree. And I'm going to try to regale you with some stories of old astronomical friends seen in new light, as the title says here. This is a talk that's mostly on the science, the astrophysics of planetary nebulae, and not so much on the techniques, the imaging techniques. But I'm happy to be interrupted and take questions about imaging techniques as well that we've used. Some of that I'll be talking about, but a lot of it I will just leave for your imagination, and we can, feel free to ask me questions later on. Let's see, is this going to work? Are we advancing? Why not? If not, okay, I'll have to hit the touch bar. Okay, so these are a bunch of beautiful images of planetary nebulae, all of which were collected in one way or another by the Hubble Space Telescope with various cameras. They were put together as this montage by Judy Schmidt. If you go to her website, she's black belt in astronomical image visualization. She dives into the HST archives, now the James Webb Space Telescope archives, and produces these lovely multicolor overlays, which are sometimes true to human vision and often not. So planetary nebulae, these beautiful objects, what are they? Where do they come from? I'm going to try to give you about 10 or 15 minutes of background on that, and then set up the scene for the research that my teams have been doing on these objects. So this is the Hertzsprung-Russell diagram. It's sort of the Rosetta Stone, if you will, that astronomers use to classify stars. We look at their temperatures, effective temperatures, surface temperatures of these stars. Effective temperature is a loaded phrase that I'm not going to bore you with, but it's sort of an effective black body temperature is the way to look at it. This is the luminosity in solar units. So the sun sits at 1 and about 6,000 degrees. So the sun sits down here on the main sequence. It is confusing hydrogen to helium in its core. That makes it a main sequence star. It will do that. It's done that for 5 billion years as a one solar mass, one solar luminosity star. That's about 5,700 degrees surface temperature. It will continue to do that for another 5 billion years. So it has a total lifetime of 10 billion years on the main sequence, fusing hydrogen to helium in its core. Planetary nebulae come from initial masses, main sequence masses, between about 80% and 8 times the mass of the sun. That's our best estimate of the mass range of an object that will become a planetary nebula late in its life. You might wonder where those numbers come from. Turns out, so that just said the sun has a 10 billion year lifetime. So we're about halfway through, fusing hydrogen to helium in its core. Only a star that's about 80% of the sun's mass at this point has had a chance to finish burning, nuclear burning of hydrogen to helium in its core before later things happen, which I'll describe. So no star that has a mass of less than about 80% the sun's is going to have had a chance in the lifetime of the universe to do what I'm about to describe. So that's where the lower limit is. These are stars that have had a chance to end their main sequence lifetimes, 0.8 solar masses since the universe began. And stars as massive as eight solar masses and above are destined to explode as supernovae. So I'm not going to talk about those stars, as fascinating as they are. I'm talking about objects that become planetary nebulae. So when a star stops fusing, runs out of hydrogen in its core, has converted almost all of that hydrogen to helium in its core, it climbs up 2 different parts of the Hertzsprung-Russell diagram in terms of its luminosity, and it becomes cooler. Those stars we refer to as red giants. But red giants come in different categories. There's a first red giant branch, you see with the RG up there. That's when a star has an inert helium core from all that hydrogen fusion that's been going on, and it's got a hydrogen-rich envelope still around it. It expands at that point. It starts burning hydrogen. When I say burn, I mean fuse hydrogen to helium in a shell around the core. It expands into a red giant. At some point, it will get to the place in the core where the temperature is high enough for helium fusion to begin, and then the star stops being a red giant briefly. When I say briefly, much less than its main sequence lifetime, and it becomes a so-called horizontal branch star for a little while. When it finishes fusing helium into carbon, so now you've got a carbon, mostly carbon, oxygen core surrounded by helium products that are being produced by the hydrogen burning shell. Are you with me? You now have concentric shells of hydrogen burning, helium burning around an inert carbon oxygen core. That's called the asymptotic giant branch. Astronomers have funny names for everything based on historical literature. So it's called the asymptotic giant branch because the star climbs back up in luminosity, asymptotically approaching and exceeding the red giant that it was. At that point, the star develops a very cold envelope, lots of gas and lots of molecular gas and dust form. So at temperatures like the surface of the sun, too hot for molecular gas and dust to form, dust being heavy molecules. But on the red giant branch, especially the asymptotic giant branch, temperatures get about half that of the surface temperature of the sun, and you get lots of gas and dust, lots of molecular gas and dust forming. That's a recipe for the star to actually start disintegrating. The dust is very good at intercepting the infrared radiation from the surface of the star, basically like solar cells pushes the envelope of the star away. So at that point, the outer hydrogen-rich envelope, but with plenty of molecules and gas, perhaps molecules and dust left over, is ejected. And now we have to take our effective temperature scale way over to the left. Notice how astronomers like to go left to right, high to low, that we do that sometimes. In this case, we do it historically because that's how the Hertzsprung-Russell diagram has always been shown to us. So the star, once the envelope is ejected, you start to see that very superheated core where the fusion has been going on. That's going to become a white dwarf. White dwarfs are some of the hottest stars known, and actually the central stars of planetary nebulae, after the star is the central core is exposed, you have a star that's a little bit bigger than the size of the Earth, but has temperatures all the way up to a couple 100,000 degrees. Some of the hottest stars known are at the cores of planetary nebulae. That core is a humongous source, a very luminous source of ultraviolet radiation. It shreds the envelope, ionizing it, perhaps dissociating molecules that were left over, perhaps destroying dust grains that were left over. That ionized gas is what forms the planetary nebula that astronomers like me who study them know and love. Eventually that planetary nebula will disperse and you end up with just a white dwarf that's doomed forever to cool for the remaining life of the universe. And it will become cooler and become dimmer. And that's why we see white dwarfs down here. All right, I'm tempted to say any questions, but I'm not going to say that. I'm happy to answer questions about the whole process at any point, especially toward the end of the talk, if you like. So this is what one of the interesting things about most interesting things about planetary nebulae and the asymptotic giant branch stars that form planetary nebulae, beginning with stars about 1 to 8 solar masses. If you look at the elements that were generated that we know and love here on Earth and provide the elements of life and everything that life needs to exist on Earth and everything we need to make up our solar system, you can see AGB stars written down in a few places here. I think I highlight them in the slide. Oops. So most of the carbon in the universe is probably produced in asymptotic giant branch stars that subsequently become planetary nebulae. So if you want interested in where the carbon in your body comes from, you went through a planetary nebula or at least an asymptotic giant branch star once in your past life. Nitrogen too, the nitrogen we're breathing in this room, a lot of that was produced in stars like those that become planetary nebulae. And heavier things too, barium, cesium, lead, Those things are produced by neutron capture processes in the core, near the cores of these stars. You need to somehow get that material out of the star and disperse it into interstellar space, or it's going to be locked inside that white dwarf forever. But it turns out that these red giant stars are churning constantly. They're convectively active. So fusion products that are produced near the core have a good chance eventually of getting mixed to the surface and then ejected. So we also see all those things in a planetary nebula after the planetary nebula has formed. All the things you see here that are produced in AGB stars. This is a schematic diagram of what a planetary nebula should consist of. Out here, you've got cold, neutral dust and molecular gas from the ejected envelope of the former red giant star. Interior to that, because the core has just been exposed recently, as in the last 1,000 years or so, in the case of some planetary nebulae, you've got a very intense source of ultraviolet radiation. It can be up to 10,000 times the luminosity of the sun, but most of it's coming out in ultraviolet because it's 200,000 degrees or more in temperature. So that ultraviolet ionizes the material. You get a planetary nebula where you see this H+, the ionized, mostly hydrogen gas with trace elements mixed in. Here's a beautiful picture of a planetary nebula taken by the Hubble Space Telescope. One thing I should have mentioned, by the way, it'll come up later. Never mind. It won't. All right, in case it doesn't come up later. The escape velocity out here, maybe this comes up later. Anyway, the escape velocity out here is for the envelope is roughly the orbital velocity of the Earth around the sun, because when a red giant expands to the place where the envelope is pushed away, it will be about as big as the Earth's orbit around the sun, 1 astronomical unit in radius. And we are going around the sun at about 30 kilometers per second. That's about the escape velocity if you just give the Earth a little extra push. So this material is expanding about 30 kilometers per second. This is an Earth-sized core that has anywhere from 1/2 to all the way up to maybe 1.4 times the mass of the sun. The escape velocity is enormous here, and you get a speed of material coming off of this white dwarf, this future white dwarf, at a couple thousand kilometers per second. That's a recipe for a shock that is shown right here, and a hot bubble interior from shocked gas. The shock just means fast material has hit slow material and heated it up. So all of that is actually shown in this Hubble Space Telescope image. If you look carefully, you can see the different layers in this more or less spherically, more like elliptically spherical planetary nebula. Out here somewhere is that cold material that was ejected from the surface of the red giant that has now cooled down to 100 or maybe just 30 or so degrees above absolute zero. Interior to that, you've got 10,000 degree ionized gas. And interior to that, in principle, you've got superheated gas from a shock with a characteristic shock velocity of a couple thousand kilometers per second. And if you just work out the math, 1/2 mv squared, where the mass is the mass of the hydrogen atom, equals kT, roughly speaking, you get a temperature that's about 10 to 100 million degrees in that inner region. Okay, look, I did show it to you. Okay, I said all this. So I'll move on. The hot bubble, temperature of at least 10,000, at least a million degrees, sorry. So early on in the lifetime of the Chandra X-ray Observatory, which some of you may be familiar with, maybe some of you are not familiar with. It's another in the NASA Great Observatory series. I worked on the Chandra project for 6 years prior to coming to RIT when I was at MIT as a research scientist. I got here 1 week before Chandra's launch in 1999, and was lucky enough to propose for and win some Chandra time in cycle 1 to look at a couple of planetary nebulae. The first one we looked at was this planetary nebula called BD +30 3639. It's the 3,639 object in the BD catalog in the declination region plus 30. That's where it gets its name. So who cares, right? It's just a faint star-like object in the sky. Turns out it has a little nebula around it. It's about 10,000 degrees, that you see in this Hubble image. When I first got this Chandra observation in my computer, I remember it vividly. I was in my office on the second floor here. I looked at the image and I went, oh my God, they didn't focus Chandra. It's out of focus. It's fuzzy. And then I went, oh, wait, that's the hot bubble. It's supposed to be fuzzy. And as you can see, it fits neatly inside the ionized gas, just as the theorists had predicted it should. This object is known to have about a 2,000 kilometer per second wind coming off of this central star that is now rapidly heating up, just like it's supposed to as this object becomes a planetary nebula.
Maxwell-Boltzmann, is it radiation pressure? Is it magnetic radiation?
What mechanism for what? Oh, from the white dwarf itself at this point. So it's radiation pressure on something. And it's in the case of the cool, Grover knows this about as well as anyone does. In the case of the cool envelope of the asymptotic giant branch progenitor star, it was radiation pressure on dust grains. At this point, it's probably radiation pressure on actually transitions in the ultraviolet. So you got ultraviolet photons that are being absorbed by heavy elements and getting pushed away. Yeah. So you can see the structure here. I flipped it over, but it's exactly the structure that the theorists predicted. Other objects were imaged early on in Chandra's lifetime. This is the famous Cat's Eye Nebula that maybe many of you have seen with the Hubble Space Telescope. By the way, I've tried to put little fiducials here, little icons for the different instruments that are being used, different missions that are being used for these images. Here's the Chandra view. I love flipping back and forth between these two. This gave a surprise. I remember getting an email from You. She said, wow, just like you found the hot bubble, we found another one. But what the heck is the bright thing in the center there? These white dwarfs are not hot enough at 200,000 degrees to be emitting X-rays at wavelengths where Chandra can detect them. So something else is going on. And I will hint there, and I'll come back to that hint in a minute if I remember. So meanwhile, Chandra has done much more imaging of objects that the Hubble Space Telescope has looked at, planetary nebulae, and in many cases, we see this central bubble. This is the result of a survey that we did, which we named the Chandra X-ray Survey of Planetary Nebula, or CHAN-PLANS, which I worked on with erstwhile student Rudy Montez. He really led the charge in many cases, getting these data. Rudy was the first graduate from the AST program here, and he spent some time in the imaging science program before transferring over. Some of you may remember Rudy when he was around. Rudy is now the one of the associate directors of the Chandra X-ray Observatory Science Center in Cambridge. So we looked at a large number of planetary nebulae over a period of time with Chandra. And you can see when you overlay them, in each case, we seem to see a hot bubble. In some cases, we see this point-like object at the central star. Here is a kind of quick overview of what we learned from the CHAN-PLANS survey. So we looked at the objects that are shown in, can't remember now. This is all of the objects, all the planetary nebulae that we could find in the catalog of a recent catalog of planetary nebulae, not so recent anymore. One of the better catalogs of planetary nebulae, shown in terms of the physical size of the planetary nebula and the distance over here. So that's kind of the sample that we picked out. These are the stars, these are the planetary nebulae we actually looked at, we picked out to look at. And here are a quick tour of the results. The stars that sorry, I keep saying stars. The planetary nebulae we found have hot bubbles, tend to be the smaller ones. They're pretty well distributed in distance, so it doesn't seem to be a distance effect is too much of a factor here for us. But we see this cutoff where if the planetary nebula is bigger than a certain size, we stop seeing X-rays from hot bubbles. We don't see X-rays from hot bubbles. But we see point sources kind of scattered throughout the size distribution here. And then you can look at the few objects that we've seen where we see both a hot bubble and a point source at the center. That's sort of the distribution. This is the HR diagram view, the Hertzsprung-Russell diagram view that I showed you in the first place, luminosity, temperature. And what we're seeing is that as these planetary nebulae make the turn, core becomes exposed, the hot bubble goes away. So hot bubbles, it turns out, is a very short-lived episode in the life of a planetary nebula that's showing us the interaction between the envelope of the red giant that was ejected and the fast wind that's coming off of the newly unveiled core. But then you can look back at this beautiful montage by Judy Schmidt, and you can see how many different shapes and sizes are represented in planetary nebulae. Doesn't matter what shape, what's your favorite shape or design, spirograph design, you know, those of you who are old enough to remember spirograph, maybe it's come back. What doesn't matter what the design it might be that you're looking for, you can find it in a planetary nebula. So what is the cause of these different shapes? We tend to just kind of try to classify them like butterfly collecting, if you like. You know, what are the different types of planetary nebula that we tend to see? We'd call this one a round one, this one an hourglass bipolar one, this one a multipolar point symmetric structure. Yes. Oh, I'll try. What was the last one? I didn't see it.
Wanted to be admitted.
Oh, okay. Well.
Okay.
Thank you. Okay. Yeah. So what are the sources of these shapes? Why are so many so aspherical? You can see that many have a sort of pinched waist structure, like the planetary nebula you see up there. I think it's Hubble 12 or something like that. You have this hourglass structure with a pinched waist. Well, the thinking is that there must be some sort of a structure that's impeding the expansion of the planetary nebula in the equatorial direction and not in the polar direction. So you could have a uniform wind coming off of the central star. It's going to have an easier time going out toward the poles than it is along the equator. And that would give you that shape that you see. And is this therefore evidence of a binary companion? There has to be some sort of source of angular momentum here to create that kind of a structure. And a binary companion is a potential source of a large amount of stored angular momentum in the system. If the sun had a small star orbiting it when the sun runs out of nuclear fuel, then the sun might turn into a structure that looks like this. Jupiter, maybe, not necessarily massive enough. Jupiter only has 0.1% of the mass of the sun. But a more massive star might be an explanation. And in fact, this is an idea that has caught on in the time that I've been studying planetary nebulae, which is now like 30 years. This has caught on like crazy, this idea that when we look at these kinds of structures in planetary nebulae, we are likely seeing binary companions as the explanation. Binary star systems. There are all kinds of things. I won't go through the whole laundry list here of things that a companion star could do, but it turns out you can get spiral structures in the ejecta from a red giant star if you have a close binary companion. You can get focusing of mass loss along the equatorial plane, which could explain these dense equatorial regions that are then where it's and then easier to clear out the polar regions than the equatorial regions if the fast wind from the unveiled central star starts up. You can get disks and jets. You can get a disk forming around the companion star. You can get jets coming off of that companion star. And you can even have a case, you can even have cases where the binary companion is swallowed by the red giant. If that happens, then all hell breaks loose, to use a technical term, and you can quickly eject the envelope of the central star. of the mass losing star, I should say. So these are examples in the literature of simulations that have been done showing this spiral pattern that will appear when a binary companion is present, and sort of shepherding the ejecta from the central star. I'm not going to worry about that not playing. Okay, and we also have very detailed simulations of the sorts of polar lobe structures that should emerge when you get these fast flows that are focused along the polar directions. And observations have backed this idea up. We see from the ALMA, the Atacama Large Millimeter Array interferometer in Chile, we see examples of asymptotic giant branch red giant stars that are losing mass in these sort of spiral patterns that are predicted. And we see these bilobe structures right after the red giant has started to transform itself into a planetary nebula. And when you look at a planetary nebula that's gotten further along, the ionization has taken place, we still can see evidence of these spiral structures in many cases, about 8% of cases. So that's pretty strong evidence for the presence of a binary companion. To kind of evaluate some of these things, a few years ago, I proposed to use the Hubble Space Telescope, the capabilities of its wide field camera 3. We knew of a couple of planetary nebulae, including the one that I'm showing you here, that are famous in the sense that this is one of the longest observed planetary nebulae in astronomy in terms of the things that we've learned about it. It's been observed for the last 60, 80 years or so. It's called NGC 7027. I was kind of astounded when I looked at the Hubble Space Telescope archive and I saw that no one had used Hubble's most powerful camera, the Wide Field Camera 3, the last one that was installed in the servicing mission of 2009, to look at this planetary nebula. So we threw the entire arsenal of filters that the Hubble Space Telescope Wide Field Camera 3 has at this planetary nebula and one other planetary nebula, the Butterfly Planetary Nebula, in order to see its nature in a bunch of different emission lines that isolate both different elements that are there in the planetary nebula and different states of excitation of the gas. And you can see the character of this planetary nebula changes radically as you move across these different emission lines. And if you put them all together, as was done so beautifully by the Space Telescope Science Institute image visualization folks, you put all these images together, color coding them in various ways, you get this kind of almost three-dimensional view of the planetary nebula. And this was work that was done by my just minted PhD student, Paula Moraga Bez. She mapped out different outflows that one can see. In this nebula, you have a real train wreck going on. It seemed to have lost mass more or less in spherically symmetric fashion. But in the last 600 to 800 years or so, very specific directions, outflows have been launched in very specific directions into the previously ejected material. And we can see that progression of spherical outflow going to fast collimated outflow in various different ways. This is one of the ways we looked at it, where you can see the Chandra X-ray emission at the core. These are images that we got way back in cycle 1 of Chandra, and then more recently, about 12 years later. And then you can see the shocks showing up in specific emission lines that are very sensitive to interactions between fast and slow winds. And as I mentioned, we did this for another planetary nebula, the Butterfly Planetary Nebula. And we got a real surprise when we used Wide Field Camera 3 to image this planetary nebula in the form of this kind of S shape that you see in blue here. That's an emission line of iron that only shows up when you have an outflow of about 100 kilometers per second. And this is surprising to us because of the directionality of that outflow. It's only heading out in one direction along the lobes, and one would not expect that based on the simple model of a binary companion. There may be a third star in the system or some kind of interaction between a disk and a star that causes precession, not unlike the precession of the Earth's tipped axis. This is a map of all the different zones that one can identify by looking carefully at the different emission line signatures that we see. And if you do an even more careful job, you can actually, by comparing our Hubble images from 2019, 2020 with images that were taken in 2009 with the wide field camera, you can actually see the expansion of the nebula. And you can see zones where gas was ejected starting about 2,300 years ago, and then most recently about 1,000 years ago. You see these distinct zones where things are moving faster than in other places, and you can actually trace all those back to the central star as distinct ejections that were made. And just a little plug, this imagery made Forbes top 5 of 2020 or something like that. I forget what class of images these were. I think they were all astronomical images. It turns out that these planetary nebulae come in different forms, not only different shapes, but different origins. We're honing in on different origins. The Cat's Eye Nebula, which I showed you earlier, has negligible masses of dust and molecular gas left. It's all ionized. All the material is ionized, and it's all about 10,000 degrees. This object that I just showed you, NGC 7027, has enormous masses of molecular gas and dust left, and you can actually see the dust. That's the red material here. It's coded red fairly accurately because what it's showing you is light that's been absorbed, where most of the blue light's been absorbed or scattered, just like the atmosphere tends to scatter away blue light and absorb and scatter blue light, leave the red light to go through. We're seeing the same phenomenon here. So that's actually a map, pretty good map of dust in the front of the nebula. Lots of dust and molecular gas. This object has been known to have a lot of molecular gas for a long time. So we actually use the NOEMA interferometer. These are two different ways to look at the data, the image data. This is the Hubble Space Telescope overlay I showed you earlier. These are different Hubble Space Telescope images from Wide Field Camera 3, our images, plus infrared camera, NICMOS, that was removed, I think, in 2009, shut down in red. Should have mentioned the red is from molecular hydrogen, so that's the molecular gas. We looked at this object with the NOEMA interferometer, which is on a mountaintop in France, in the Alps. It's an array of about a dozen radio telescopes. And we looked at transitions of carbon monoxide and ionized carbon monoxide, which is telling us where the ultraviolet from the central star is now ripping apart the molecular gas as it proceeds into interstellar space. We also looked at HCO+, so ionized CO with basically CO when you add a proton to it. This is tracing X-ray emission that's coming from the central regions and ionizing the gas around it, the molecular gas around it. And we can also use the Atacama Large Millimeter Array to look at the molecular gas, in this case, in the Butterfly Nebula. And this is just a montage of carbon monoxide, hydrogenated carbon monoxide, and hydrogen cyanide emission from the central regions of the Butterfly Nebula. And that's showing us again that there is indeed this dense torus of material that surrounds the equatorial region. And that equatorial material, that molecular gas, is being bombarded with high energy radiation, which is ionizing it and actually doing some very interesting chemistry. So we're seeing the chemistry that's going on in these objects, and these chemicals are going to wind up being dispersed into interstellar space, where they can be incorporated into fun things like human beings eventually, perhaps. So one of the objects that was looked at, the JWST, the James Webb Space Telescope, observed in the very first days of its operation, of its science operation, was a planetary nebula. The planetary nebula that goes by the name Southern Ring, or NGC 3132. And it's very interesting. It was very interesting to me when this came out because you see here the images from the near infrared camera and from the mid infrared camera on JWST. And it was definitely showing us a totally new view of this planetary nebula. I and some of my colleagues were not so happy about the fact, well, that's kind of a crude way to put it. We would have liked to see the images shown in a different form. Just showing the near infrared and the mid infrared images as montages like this doesn't necessarily show you what's physically going on in the object. So as soon as I could, I grabbed the images from the archive and rearranged them so that you see the ionized gas and the molecular gas. These are filters that were used both in the near infrared camera and in the mid infrared camera. And same here, a couple of filters in the near infrared camera, one in the mid infrared camera. But now the filters are isolating ionized gas. These are transitions of recombining ionized hydrogen. This is a transition of sulfur, twice ionized. This is molecular gas, molecular hydrogen, just with at different wavelengths, different transitions of molecular hydrogen. So this is like Jekyll and Hyde. This object has two completely different personalities. It has a compact, hot, ionized region. It's got a cooler surrounding molecule-rich region. And we're seeing that in gory detail now when we look with JWST. We also noticed that there's a binary central star, quite obviously, and there's a ring or spiral system that hadn't shown up before. This binary companion, if you look carefully, there are two stars there. They're probably too far apart for the binary companion to have influenced the way that the mass was lost. So there must be more than two stars here. There must be at least three stars to be able to set up a ring system in the nebula as well. So we used subsequently to the JWST imaging coming out in JWST's first image release, we used the submillimeter array on Mauna Kea to look at carbon monoxide in the Southern Ring Nebula. The only previous maps of carbon monoxide in the Southern Ring were obtained more than 30 years ago. It was kind of astounding to me that no one had bothered to look, in 3 decades, had bothered to look at this object, which is pretty well studied otherwise. And those images were taken at 20 arc-second resolution, which is not so good when you think that the James Webb Space Telescope gets sub-arc-second resolution. So we wanted to see if we could use the carbon monoxide to trace the mass loss from the former red giant star, maybe look for better evidence for this interacting binary companion that we think might be there. So we used the submillimeter array on Mauna Kea, which is a set of 8 6-meter telescopes, relatively small telescopes, but 8 of them that can be spread out pretty far apart to form an interferometer that can get resolution more like 5 arc seconds, and we can get velocity resolution of 2 kilometers per second. So we can see red shifts and blue shifts in the gas, this carbon monoxide gas, of order 2 kilometers per second. James Webb Space Telescope cannot do that. You get all the emission from molecular hydrogen regardless of the red shift or blue shift. With carbon monoxide imaged with an interferometer, you can actually see the red shifts and blue shifts. When we do that and we compare the James Webb Space Telescope images, molecular hydrogen on the right here, with the carbon monoxide images, we start to see the 3-dimensionality. Blue is material coming toward us, red is material moving away from us. But a better way to look at this, so those are the 2 ways we looked at it. A better way to look at this, if it cooperates with me, is by taking the data cube, position, velocity, and position in 2 directions, velocity in another direction, and actually just rotating it. So that's the 3-dimensional structure of the Southern Ring Nebula, which you cannot possibly see unless you look at the carbon monoxide gas and you carefully pick apart the velocities using red shifts and blue shifts. When you look at this, it struck me immediately, the ring that you see, it's got these 2 kind of bright patches on either side. There's a second ring in there. It's almost perpendicular to the main ring that we're sort of seeing when we see the JWST images. There's a second ring in there that's perpendicular. And when you look at it, with the velocity axis collapsed, you see this. That second ring becomes apparent now once you've been able to flip the thing in 3 dimensions. So here is the Ring Nebula. That I was just showing you the Southern Ring Nebula, which is too far south for us to ever see from Rochester. But the Ring Nebula in the middle of the summer is sitting almost right overhead. It's in the constellation of Lyra. So one of the brightest stars in the northern sky is Vega. It's almost right overhead in the summer. And this nebula is sitting kind of close by. If you have a reasonable small telescope, like anywhere between 3 and 6 inches, and you look at this at Lyra and you look in the right place, you will see the Ring Nebula. I saw this when I was like 12 years old. And it would kind of blew my mind at the time because you see a bunch of stars and you see this little smoke ring. You wonder what the heck is going on with that one object. This is the famous Hubble Space Telescope imaging that was done about 12, 15 years ago now, appeared in a paper by Charles Odell in 2013 and in a press release. So we understand what the Ring Nebula looks like through telescopes, but we don't know much about what the 3-dimensional structure is, or I should say we did not know much about what the 3-dimensional structure was. Is this a smoke ring? Is it a soap bubble? Is it an ellipsoid? What kind of shape are we looking at here anyway when we look at the ring? The ring is also the archetype, one of the best examples we have, of a molecule-rich planetary nebula. You could see the dust in here, and each one of these little blobs of dust is a rich reservoir of molecular gas. But again, this starts to sound familiar, right? Like with the Southern Ring, the Ring Nebula, nobody had bothered to look at it in 30 years in carbon monoxide gas. And now we've got powerful interferometers. So this will look familiar. When the JWST images of the Ring Nebula came out, we thought, well, maybe we should take a look with the submillimeter array like we did for the Southern Ring, all the same things. About a year after we got the Southern Ring data, we got the data for the Ring Nebula. The SMA project liked this so much when they saw our first few images, and we were going, wow, there's a lot of structure in there, that they gave us extra time and we could use the SMA in its more extended configuration to get higher resolution images down to about 3 arc seconds in resolution. And let's see if this works. There's a movie here, which some of you may have seen already, which appeared in a press release because I gave a press briefing on this at the American Astronomical Society in Washington, D.C. a couple of weeks ago. The press folks here and Jacqueline were kind enough to get this all organized for us, and with some help from the Harvard-Smithsonian Center for Astrophysics, putting in a QR code for me. We've got the video there for the taking, so you can grab it if you want, or you can just go to the YouTube channel. Okay, here it comes. I'm going to try to, I think it's going to play. I'm going to try to, yeah, I'll narrate as you watch the movie. So this is again, the HST visible light image in ionized gas. The Ring Nebula is among the most photographed celestial objects in the sky. And James Webb Space Telescope, during its first year of operations, looked at it in molecular hydrogen. So this is hot molecular gas, a couple thousand degrees probably. It's being heated nicely to show up in the near infrared. And we also saw dust and the central star. This is the image, 2-dimensional image, that we got with the submillimeter array. So the collapsed along the velocity axis. And it looks like a molecular hydrogen image, more or less, but we can get a 3D view again. So we've mapped the millimeter wave radio emission, and because we've got reasonably good velocity resolution, we can measure the blue shifts and red shifts. So we get a third dimension of information. Because the Ring Nebula, this is the data cube shown to you in position XY versus velocity. Because we know the Ring Nebula is the expanding remnant of a dying sun-like star, a former red giant, asymptotic giant branch star, we know the clumpy gas that you're seeing here is in an expanding shell. So we can actually build a simple geometrical model. And the simplest thing I could come up with, basically my primitive Python coding skills, is an ellipsoid, a triaxial ellipsoid. It actually mimics the surface of this CO pretty well. So it traces the surface that the CO is sitting on, a triaxial ellipsoid. That was kind of a surprise. But we can use that model to say that the gas was ejected about 6,000 years ago, but there are holes. Clearly, there are holes. And the holes, it seems, must have been generated by a fast outflow that was coming along the poles and was ejected after the triaxial ellipsoid. It's also tilted with respect to the triaxial ellipsoid. All of that's pretty hard to explain unless there's at least two stars. So the red giant star ejected its outer layers, forming the main ring, and probably interactions with a companion star have generated high velocity flows that are coming out the poles. And it's hard to see those flows directly, but if you notice, there are these little blobs sitting inside the holes. So if you compare now very carefully the molecular and the ionized gas, because we have the JWST images showing it's the ionized gas in the light of twice ionized sulfur, we can see now that the carbon monoxide, the molecules, are like a skin around the ionized gas. That's not terribly surprising, but the width of the skin was surprising to me how thin it is. It's sitting outside the ionized gas completely. Furthermore, we know now where the central star is, and this has been the source of a little bit of confusion when looking at this nebula. In fact, the central star does sit at the geometric center of the nebula, but you can find plenty of papers in the literature where people have said, oh, the central star is kind of offset in the nebula. And that's just a function of the fact that the nebula has these holes, and the holes are tilted with respect to our viewing angle. So it looks like the star is a little bit off center, but it's not. And then we also get an indication of these high velocity blobs of gas and dust, red shifted moving away from us, blue shifted moving toward us at about 50 kilometers per second. So faster than the ellipsoidal shell. That's material flying through at high velocity. And then just because I could, I was using iMovie. I did some credits here to see the spinning ring nebula again in 3 dimensions. This is the paper. This paper was accepted faster than any paper I've ever submitted in my life. Less than a week from submission to acceptance. I actually was worried. I'm like, did the referee really read this? I don't think so, but okay, I'll take it. I submitted at 11:30 on the night before the press briefing, and it was accepted the following Monday or something nuts like that. Anyway, okay. We are just about out of time. It's about 10 of, and I'm just going to leave you with these tantalizing new images of 2 planetary nebulae that we call extreme bipolar planetary nebulae, where we see the archival JWST image, archival HST images, our new ALMA data. So my student Paula, who just finished her PhD, is hard at work on a paper that hopefully will hit the streets in a month or two on the Atacama Large Millimeter Array imaging, where we see the molecular gas that's at the cores in the equatorial tori that are shaping these nebulae. And now we've got new James Webb Space Telescope images of these 2 planetary nebulae. We managed to sneak in a couple of observations in there. I won't go into the details, but I think we just got lucky and got the data. JWST is oversubscribed by like a factor of 10 or something like that in terms of proposals versus time allocated. So still very lucky, and now we're seeing these nebulae in totally new light, and I'm blown away, and I don't know what to do except I'm trying to like wake these up as fast as I can. You see again molecular hydrogen on them too, so there's a shock happening just like with the butterfly nebula I showed you earlier. It's a very similar nebula apparently, but with a different inclination angle, pointed in a slightly different way. This one really blew my mind. Molecular hydrogen is obviously a spherical shell. So that's now we're seeing how a planetary nebula can eject, or the red giant can eject material in spherically symmetric fashion and then start blowing a fast wind in a collimated way. So that's telling us a lot. It's giving us a lot of information about how binary systems that include a red giant star would evolve. I'll leave it there. Thanks for your attention. I'll bring up the lights. Happy to answer any questions there. Any questions on the Zoom? Yeah, go ahead.
So do you know why planetary nebulae have X-ray emission?
So 2 reasons. Oh, okay. There's the shock that generates the diffuse emission. You're right. I never actually said it, did I? So the fact that some planetary nebulae have point sources is very strong evidence for the presence of a binary companion. You can't explain X-rays at the energies that we see with Chandra from a proto-white dwarf that's even as hot as 300,000 degrees. There isn't enough soft X-ray emission to be detectable with Chandra. So that means there has to be higher energy X-rays, or higher energy source of emission. And the most logical explanation is the X-rays are coming from the corona of a companion star. Like the sun puts out about 1/100000th, 1/10,000,000th of its total energy in X-rays from its corona. But a star that's managed to accrete angular momentum from the red giant and has been spun up, those stars can have coronae that are 1,000 times more powerful, and then we could detect them with Chandra. So very likely, to make a long story short, we're seeing the companion star in X-rays.
So basically, it's caused by the accretion of the companion.
Yes, indirectly. It's the accretion of angular momentum that spins the star up, and if you have a convectively active star with that's spinning fast, you get a magnetic dynamo like in the sun, but cranked up so that you get 1,000 times stronger corona around it. That's the best explanation we have going, and no one's been able to say it's wrong so far. Yeah, great question, Robert.
Probably become very good at the very center, right in things.
Yeah.
See it wobble.
That's a great question too, and the problem is, barely see. Here's the central star. That central star is like 10,000 times the luminosity of the sun. So two answers, right? You can't directly detect a binary companion because this star is too bright. The wobble, these stars tend to be kind of featureless in their spectra. In order to detect the wobbles, so a normal star like the sun has deep absorption lines. And you can watch the absorption lines go back and forth as the unseen companion, like a planet, moves the barycenter, sorry, I said that wrong. The star orbits the barycenter, right? And so you're seeing that wobble. You can't do that with these objects. They don't have the right spectra to allow you to do that. Asterisk, there's a subset where some indications of binarity from wobble is seen. Often you're seeing the fact that the central soon-to-be white dwarf is gravitationally distorted by its companion, and so as it goes around, it gets fainter when its axis of symmetry is pointed toward you, and brighter as its axis of symmetry is perpendicular to you, because you see more surface area. So you can see a photometric signature. But those examples are few and far between. The hit rate on binarity on these objects is very low. Direct evidence for binarity. It's a frustrating problem. Well, thanks again, and see you around.